Hey kiddos, welcome back to week number 2 of virtual learning. Today we're going to debrief the photoelectric effect simulation that I asked you to participate in, and hopefully you guys all have made some graphs of kinetic energy of the electron versus frequency. All right, so today's goals, we're going to debrief the photoelectric effect PhET. We're going to apply the photoelectric effect equation that comes from the graphs that we made to problem solving, and we're going to discuss technology that uses the photoelectric effect. Okay, so in your simulation, you should have come up with three graphs. You would have seen them on the sidebar in the simulation. And so a couple of things that we can get from these graphs is that there is a certain limit at which you can get current flowing through the device. So if you take a look right here at -6 volts on the battery, at any higher negative voltage, so anything a voltage larger than 6 in the negative, you don't get any more current. And you can also see that the current increases up to a certain point and then it just levels off. Okay, so what we call this right here, the first point at which the current is 0, this is called the stopping voltage, right? The first point at which current is equal to 0. Okay, and it increases linearly up to some limit for the current. Okay, and then when we're talking about energy of the electrons that are emitted from the target, we can see that there is also a limit for the frequency. Okay, so there's a first frequency at which we actually see moving electrons that are emitted from the target. Okay, so this frequency is called the critical frequency. Okay, this is the first frequency at which we see electrons liberated from the bounds of the target material, and we abbreviate this with F sub C, right? The critical frequency. And then we notice just generally that current increases with intensity. So the brighter the light is, the more current we'll see. And we notice that current is proportional to intensity, but really we weren't looking at like the wave model of light necessarily, right? We were looking in the simulation, light looked like little particles themselves, right? So current was equal, it was proportional to the intensity of light, which is the number of photons. Okay, so we're seeing that there's some pretty surprising things happen. And we're seeing that we get more electrons emitted from the target material if there are more photons of light hitting that target material. It's almost like there are collisions going on. And we're also seeing, if you took a look at the emission spectra demo on YouTube that I posted, like we would expect that light going through a diffraction grating would make an interference pattern. We'd see dark and we'd see light spots, but we would expect those to be evenly spaced with a bright central maximum. And that's not what we were seeing in that video. We were seeing kind of what seemed to be randomly spaced dark and light spots. So in these circumstances, it's looking kind of like our wave model of light is breaking down and explaining what's going on in the photoelectric effect and also in the emission spectrum of light. Okay, so from all of this, like I said, we get some surprising observations, and there are three big ones. So the first surprising observation is that the intensity of incident light does not affect the energy of the emitted electrons. Did you guys see that the intensity, right, impacted the number of electrons emitted, but the intensity didn't make those electrons go faster or slower, right? It didn't give them any more or less kinetic energy. The second surprising finding was that the electron energy did depend on the frequency of light, with a minimum frequency below which no electrons were emitted. So energy was related to frequency. The number of electrons emitted was related to intensity of light. And then we saw that the electrons are emitted with no time delay, which is kind of crazy because we know that when materials heat up, they emit electrons also. So if we were to, like in our light bulbs, if we had a filament light bulb, if we ran current through that light bulb, the filament, like the little resistor that ends up emitting light in those old style light bulbs that we use for the Young's double slit experiment, if we heat those up, atoms that get hot enough have free electrons that can be emitted. They're free to go anywhere, and if you expose them to a potential difference, then they can travel from one place to another. But it takes time for those materials to heat up, and those electrons are emitted after a period of time. But here, it seems in this instance that the instant that the correct frequency of light hits that target material, electrons are emitted with no time delay. Right? This isn't a matter of the material heating up. It's something different that's going on. Okay, so to explain our observations, Einstein theorized that light comes in particle-like packets of energy called photons. Okay, so instead of treating light like a wave, we're treating light like a particle. And this is a phenomenon called wave-particle duality that we'll talk about next class. But what Einstein theorized was that a photon interacts with only one electron, and you can think of them like two particles that are colliding. And the photon imparts its energy to the electron, just like two particles, like two balls, would impart their energy to each other in a collision. Okay, the photon energy depends on its frequency, right? So energy, photon energy equals this lowercase h, which is Planck's constant. Okay, and the lowercase h Planck's constant is 6.626 times 10 to the minus 34 joule seconds. That can be written in terms of electron volts also. Just if you remember that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So there are that many joules per electron volt. Okay, so you would just want to divide Planck's constant by 1.6 times 10 to the minus 19, and you'll get the constant in electron volts as needed. Now, you may have seen this equation in chemistry class, looking at energy of photons, especially if you studied emission and absorption spectra. And so we're taking the physics view. I have a 10-year long argument with Mr. McQueen about this. He, in chemistry land, tells me that this equation is equal to E equals H nu right? It's a curvy V. That's how you guys write it in chemistry. In physics, we call frequency F because for once, the abbreviation makes sense. Okay, so we're just gonna go my way or the highway on this one, and I'll just keep arguing with Mr. McQueen. All right, so let's take a look at the graphs that you should have produced. I did see on the Google Classroom that a few of you did produce graphs from the simulation, but there were some conversion issues there. So I'm gonna draw up what we expect those to look like. All right, so I asked you to graph, whoops, I would prefer that to be black, please. Okay, so we're looking at kinetic energy of the emitted electron in joules on the y-axis, and I was looking for frequency of the light that was incident on the target material in hertz. And you were able to choose, excuse me, whichever target material you wanted. And so what we've got here is you should have gotten a proportional or a linear line like this, right, that has an x-intercept that's positive. Okay, and you should have noticed that there's no kinetic energy for your electrons up to this specific frequency, and then at that specific frequency the energy increased linearly with frequency. Okay, so at this point right here, I'm gonna label it in purple. At this point where that transition happens, this is our critical frequency. Okay, and then, so this is the actual line that we came up with. If you take this linear trend and you extrapolate it downward, you'll actually get a y-intercept right here. That's negative. Okay, and this y-intercept is actually, it's abbreviated. I know, we've seen this abbreviation before, but this time, this symbol is not electromagnetic flux. It is what's called the work function. Okay, it tells us how much work or how much energy is required to get that electron out, right, of the material. So how much work is required by a photon to liberate the electron from the material that it's bound to. Okay, so it's almost kind of like digging an electron out of a hole before it's able to have any kinetic energy of its own. Okay, so the work function, whoopsies, I want to try that again. I would like these to be green. The work function, right, the amount of energy required to liberate an electron from its material, and the critical frequency are material dependent.